We're going to talk about exponential functions in this video, and we'll just see how to graph some kind of basic exponential functions. So first, I just want to talk about the form of an exponential function. So when you see an equation for an exponential function, it will be in the function notation f of x equals b to the power x, or y equals b to the power x equivalently. So basically you could see a function like f of x equals, 5 to the power x, or y equals 3 to the power x. The important thing to note about these exponential functions is that the variable x in this case appears in the exponent. That's what defines an exponential function. Also want to point out that the base, which we're calling b in this basic form, so in these examples it would be the 5 or the 3, the base has to be a positive number, and the base can't equal 1. The reason the base can't equal 1, if you have y equals 1 to the power x, 1 to any power is just 1, so that's really y equals 1, which would just be a horizontal line, which isn't an exponential function. So that's why we can't have y equal to 1, or the base equal to 1, rather. Okay, so first we're going to look at example number 1 here. I want to graph this basic function f of x equals 2 to the power x. So over here on my graphing calculator, the two buttons that I'm going to use the y equals button, and once I fill in my equation, I'm also going to use the trace key. So those are both up at the top of your screen on your graphing calculator. So I'll start off by hitting y equals, my base 2, the caret key, which is over here to the right under the clear button, so the caret key, and then your x, your variable key, next to your alpha button up at the top left of your screen. All right, so 2 to the power x, I'm going to hit the graph button, and that's what my exponential function looks like. So here's where the trace function comes in. If you hit this trace button up at the top of your calculator screen, this trace button, what that allows you to do is type in different x values, and it will spit out the paired y value. Sorry for the zoom, that was weird. All right, so let's pick a few x values, maybe x equals -2. So I'm going to type in my calculator x equals -2. I'll hit the enter button, and I can see that y equals 0.25. So that's one ordered pair I could graph. So -2 for x, and then 0.25 for y, so just a hair above the axis there. Let's pick x equals -1. I'll type -1, hit enter, and y equals 0.5, so -1 and 0.5. If x equals 0, I get y equals 1, so there's the ordered pair 0, 1. If I have x equals 1, 1 and enter, y equals 2, so the ordered pair 1, 2. And if x equals 2, then y equals 4, and so on. 2 to the second power is 4. So I've got that ordered pair 2, 4. So you can see as I'm plotting this, it creates this curved shape. So it's a nonlinear function. And if I connect the dots, looks something like that. All right, so that's my basic exponential growth function, and I'm using the trace key to crank these out, but of course we could do these by hand. So for example, this ordered pair 1, 2 comes from the fact that our function is f of x equals 2 to the power x, or y equals 2 to the power x. So if I have y equals my base 2 raised to the power 1, that gives me my y value of 2. So when x equals 1, y equals 2. You could do that with any of these numbers. I also just want to remind you about how these negative exponents work, in case you forgot, you're a little rusty. So in this case, y equals my base 2 raised to the power -2 if -2 is x. Remember that negative exponents just change your location, so this is equal to 1 over my base 2 to the power +2, which would be 1 over 4, and 1/4, of course, is 0.25. So I just wanted to refresh your memory there. Okay, so we've got this exponential growth function. We say it's a growth function because as x increases, y increases. It's getting bigger. And let's fill in the rest of this info down here. So it asks for the domain. Domain, remember, is for our x values, while range is for our y values. For x, I happen to pick -2, -1, 0, 1, 2, but I could have picked any x, right? I could plug any x value. There are no restrictions there. So my domain is always going to be all real numbers for these exponential functions, from -infinity up to +infinity. And then we, of course, use rounded parentheses because you can't equal infinity. All right, in terms of the range, that's going to be my up and down movement. If you see how low the graph goes, we get stuck here at what's called an asymptote, actually. So you can see there's this barrier where the graph is kind of petering out at what's called a horizontal asymptote. So the value of that horizontal asymptote, the y value, would be 0. We're never going to get a y value that equals 0 or that is less than 0. So if you think of putting different exponents up here, different negative exponents, 2 to the power -1,000,000, it's going to be a teeny tiny infinitesimal number, not quite 0, but it's going to be pretty darn close. So for the range, I'm going to put rounded parenthesis 0 because we can never equal 0, but it'll get pretty close. And then as the graph increases, remember we have this exponential growth function, so the graph keeps going up and up and up. There's no boundary, so we have a range from 0 to infinity. The horizontal asymptote I already sketched out with this dashed horizontal line, so you can see that dashed horizontal red line. That horizontal asymptote's equation would be y equals 0. The horizontal line, y equals 0. Make sure when you write your asymptote, it's always as an equation. So notice that the asymptote isn't 0, it's y equals 0. Make sure you always write it in equation form. Okay, so that's our growth function. Let's take a look at our exponential decay function. So again, I'll fill in this xy table. So now over here, I want to graph f of x equals 1/2 to the power x, which is actually equivalent to 2 to the power -x. Remember how those negative exponents work. I'll write this up here. So remember how these negative exponents work. If we have f of x, or equivalently y, equals 1/2 to the power x, then by the power rule, we could write this as y equals 1 to the power x over 2 to the power x. But like we said before, over here in red, 1 to the power x is just always 1. So this just gives me 1 over 2 to the power positive x. And that expression is mathematically equivalent to 2 to the power negative x. Remember how these negative exponents work. All right, so that's how we go from 1/2 to the power x equaling 2 to the negative x, again, just as a refresher. All right, so for this exponential decay function, I could type either of these versions into my graphing calculator. I'll go back to that y equals key, clear that out. And I'm going to go ahead and use that version circled in blue. So base 2 raised to the power, so the little caret key. Then I'm going to hit my negative key and x, so 2 to the power negative x. Let's take a look at our graph. And again, we can use our trace function. So I'm going to hit the trace key. And I'll put in the same x values as before. So let's try x equals -2, hit enter, and that gives me a y value of 4. X equals -1, gives me a y value of 2. X of 0 gives me a y value of 1. X equals 1, y equals 0.5, and x equals 2 gives me y equals 0.25. Okay. So let's go ahead and plot these points. -2, 4, -1, 2, 0, 1, 1, and 0.5, so about halfway down, and then 2, and then 0.25 for y. And again, if we connect these dots, get this kind of non-linear curvy shape here. Sorry, that's a little bit squiggly. Pretend like that's a little better drawn. All right, so we have our exponential decay function. So comparing to this guy over here, for our growth function, as x got bigger, as x increased, y also increased. Over here, as x gets bigger, we go from -2 up to +2, for example. Notice that y is decreasing, right? We're getting closer and closer to that x-axis there. Okay, so notice that we still have that asymptotic behavior. We still have that horizontal asymptote down here. So I'm going to represent that with a dashed horizontal line. And we've still got the same domain as before. It doesn't ask for this below, but I'll go ahead and fill it in anyway. So my domain still goes from negative infinity to positive infinity. My range, I'm using R for range, goes from 0 to positive infinity, just like before. And my function has been transformed. We have a reflection across our y-axis, right? It flipped across that y-axis. So my transformation that I'm seeing is a reflection. So it reflects across the y-axis. That's a result of this negative x exponent, right? We went from 2 to the x to 2 to the power negative x over here. And if we wanted to represent our horizontal asymptote, which again it doesn't ask us for, but I'm going to go ahead and write it in. Our horizontal asymptote is again the equation y equals 0. Okay, so same domain, same range, same horizontal asymptote. We just have a reflection with that negative x exponent. All right, let's take a look at these last two examples. And for number 3 and number 4, I went ahead and just kind of did these advanced in my calculator. But I'll show you how I would type in number 3, so clear that out. So now we have 2 to the power x, so 2 raised to the power x. Then I'm going to hit the right arrow key on my calculator so that I can type -3. And notice that I want that big, not up in my exponent, but down low in the main equation. So 2 to the power x and then -3. There's the graph, and again, I can use the trace key. So if I type -2, there's my -2.75 for y. For this last point, if I type x equals 2, I get y equals 1, and then I just filled in the dots over here. So the transformation compared to my original function, which is straight up above, my transformation is, we've got the same graph, it's just shifted down 3 units, which we expected from that -3, right? So our transformation is a vertical shift down 3 units, vertical shift down 3 units from that -3. The domain, we can still put in any domain. You'll see that with all of these exponential functions. So any x value means the domain is all real numbers, negative to positive infinity. And then for the range, remember before we had a range from 0 to positive infinity. Now we've shifted that down 3 units. Our y values all went down 3 units. So now our range goes from -3 to positive infinity. I'm still using that rounded parenthesis because I cannot equal -3 for y, just like I couldn't equal 0 for y up above. And we still have that asymptotic behavior, that horizontal asymptote, but instead of being at y equals 0, where it was before, that red dashed line, it shifted down 3 units. So now it's down here. So my new horizontal asymptote shifted down to y equals -3. All right, over here for number 4, typing this into my graphing calculator, clear that out. Now I want everything to be up in the exponent, so 2 raised to the power, and then I just type x -3. I want that all up in the exponent. I hit graph. And in terms of my transformation, because I have x -3, I'm expecting a shift to the right 3 units, a horizontal shift to the right 3 units. So because of that, I knew that if I kept typing in my x equals -2, x equals -1 using the trace function, so if I type in x equals -2, it's just a really tiny number. I don't even know how to plot 0.03. So I went ahead and shifted my x values over a little bit. So I started with x equals 0, giving me y equals 0.125. X equals 1 gave me y of 0.25, all the way down to our final ordered pair. So using that trace function, x equals 5 gives me y equals 4. I plotted all of those points here. All right, so we have a transformation of the right 3 units. Domain continues to be negative to positive infinity. My range is back to 0 to positive infinity. And now I can see my horizontal asymptote is back to y equals 0, like numbers 1 and 2.